Okay, this is Mr. Sitta. I'm going to be talking about the trends for ionization energy. This is Coulomb's law, which we've been talking about all year long. It can be used for many things. Force equals a constant times Q1 times Q2 charges over distance. Now, D corresponds to your size, and Q corresponds to your Z effective. So as my Z effective, my Q goes up, the force required goes up. That means you need more energy. As the size decreases, the force goes up. So ionization energy is high. Ionization energy is high when the Z effective is high and the size is low. So as I go to the right, as this thing gets smaller, I'm less likely to lose an electron. Metals, highly likely to use it because you got a low Z effective. Non-metals, highly unlikely to lose it because you have a high Z effective. The Z effective makes the charge, the size small. So ionization energy, as you go to the right, it increases. Okay. Up and down. Now up and down, the Z effective is going to be a constant, but I got two things going on. I do have an increase in shielding effect, which is expressed by a constant Z effective. The S goes up. But the biggest thing is size. As I go down, the size gets bigger. As your size gets bigger, your force gets smaller, and that makes your ionization energy decrease. So going down, ionization energy decreases. Okay. Electron affinity. Electron affinity is the energy change. I might mention all my ionization energies, because they're all endothermic, they're all positive. Okay. Energy change when an atom gains an electron. So if I have something like X and it gains an electron, now it becomes negative X plus, this is exothermic, it releases energy, commonly exothermic. Okay, so again, this is important to have a high electron affinity. These are equal to your nonmetals. Where metals have low ionization energy, nonmetals have high ionization energy. Okay. I did the sample equation up here. So electron affinity, as your Z effective goes up, someone doesn't know how to use their inside voice. As your Z effective goes up, your energy electron affinity goes up. Okay, and as your size decreases, that causes it also to increase. So things that are up high here tend to have a high affinity for electrons. Well, that's because that's why your anions, your nonmetals, become anions. Your metals become cations. They lose electrons, they gain electrons. Up and down, the same trend. As your size goes bigger, that decreases your affinity for electrons. When it comes to metals, it's strictly high ionization energy. When it comes to nonmetals, and I said that wrong, When it comes to metals, tends to be low ionization energy. For metals, the property is high electron affinity. Now, electron affinity, let's look at these graphically. So, and I have nice graphs. Here's your trends with size. As you tend to go to the right, your size decreases. As you tend to go to the down, your size increases. What becomes difficult is if I was to compare, say, sodium to silver. You know, how do the sizes compare in this direction? Okay. Some of the transition metals can be, even though they're very down, they can be smaller than the alkalis. Why? Because they have a lot more protons. They have a higher Z effective.
So are you going to try to get your hair done now?
Okay.
You can call them. My boss is I have to go to the room. He's throwing stuff out.
The all right. I had to throw something over there. Totally oblivious. All right. This is why transition metals, okay, because they have so many protons, it's why they're not as active as alkali metals. Although they have, you know, they'll have a Z effective commonly of +2, they simply have a lot more protons, and so those holds those electrons in place. Okay, makes them a little unique. So that tends to be size. You will see the first 1, 2, 3, 4 shrink, and then it goes up and then kind of even. So there's not much difference in the size in a lot of your transition metals. Okay. I have these all posted online. This is just visually. You can see go down, size gets bigger. Go to the right, size gets smaller. It's just easy to see. You don't see a lot of changes in the inner transition metals because they have the same outer electrons, and their Z effective is kind of constant, so their size is kind of constant. What's different about them? When you go down, these actually do get smaller because you're getting more inner core protons. Your effective, you get more Z, more numbers of protons. Okay, next one. This is ionization energy. As we said, as you go to the right, it increases. As you go down, it decreases. You will see a couple small steps in it that I actually didn't give you a lab to do, but in a lab. And when you go from the S to the P, instead of going up, it slightly goes down. And that's the stability. They call it the stability, but this is a full shell. And the reason is these two tend to repel the first one coming in. So the S's repel the first P. And it only gets one extra proton. As you get more protons, it overcomes that trend. Starts going up again. And then you go, the first three, the first two would go into an S2. And then you go 1, 1, 1. The first dip is caused by these two repelling this one. But as you go to add it, 1, 2, 3, it goes up with nitrogen, and suddenly with oxygen you get a dip down. Now that dip is expressed as the repulsion of the one electron in the shell to the other. So that's a bit of an anomaly. You get it here, P going to S, instead of going up it goes down. It's because what we said, half full shells are more stable. There's no electron repulsion. And so this is seen as the next one going in, having some repulsion, which makes it easier to kick it out, that makes it easier to ionize it. Now, suddenly that anomaly disappears as you go down. Like you don't see the anomaly anymore. The reason the anomaly disappears is because as you go down to the 5th level, the atom is so big that there's less repulsion. So as your size goes down, that trend disappears because the trend was there from repulsion of electrons. And simply put, if you have a bigger orbital, you have less repulsion. It's kind of led to some recent discoveries. Okay, now, if I do affinity, when I fill my first S2, suddenly the affinity almost drops to 0. Okay, so I don't have a graph for affinity, but affinity is different because it's negative. So as you have a higher affinity, that's seen as a higher negative charge. And finally, your noble gases would have a 0 affinity because their shells are full. There's nowhere to put them. So we're not even going to talk about affinity then on the test or in the worksheets. Affinity was scrapped, and they replaced it with electronegativity, which I've been talking about for a while. Electronegativity is the relative attraction of an atom to an electron. And it's on a 0 to 4 scale, with 0 being low and 4 being high. And electronegativity follows a much easier pattern, and you don't see the anomalies in it. But as you go to the right, again, as you're getting smaller, your electronegativity is going up, okay? And also, as your Z effective goes up, your electronegativity is going up. So it's really determined by size and Z effective. Again, up and down. As you're up, as you're small, you get a high electronegativity, and as you're down, you get a low. In general, metals have low electronegativities, non-metals have high electronegativities. That's why metals become positive. They tend to not lose them, not gain them. Non-metals become negative, anions. Cameras, better check it. Okay. Shielding effect is the shielding of the outer electrons by the inner electrons. I also have these on notes, so all the answers are on these. I explained the Z effective already. Electronegativity is what determines what kind of bond we form, and it's the differences in electronegativity that are important. But I'll talk about that later. Okay. All your trends, increase, increase, increase. Ionization energy, electron affinity, electronegativity, they all increase. And the reason for these three increases are increasing Z effective and decreasing size. Okay? So it all starts with Z effective and size. So everything up to the upper right is increase, 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 except for size. Shielding effect, constant. That makes it not so hard to remember. Lower left, everything is decrease, 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 except for size. Lower left, size increases. The size is the one thing that goes against it. That's because of the Coulomb's law. It's inversely proportional to the force. Okay, the only thing we have to know is that Z effective is constant, which isn't hard to remember if you know the numbers on top, that they stay the same. So electronegativity decreases. And then if I ask you what's the most reactive metal, you would say to the left and down. That's the one that's most likely to have it's the one that has the lowest ionization energy. Now francium is radioactive, so we usually just go ahead and say cesium. The electronegativity of cesium is 3.3, sorry, 0.7 cesium. The highest electronegativity, we're going to ignore the noble gases because they have a full shell. They don't have a high electronegativity because they don't have anywhere to put electrons. Okay, so the highest electronegativity is fluorine. So fluorine is a 4.0. So the biggest difference between the two is 3.3. If you have a big difference, you're more likely to be ionic. If you have a low difference, you're more likely to be molecular. Okay. So I would say on a test, I would give you this sheet and I would say, fill out this sheet, know all these trends. And if you have this in front of you, you're going to be fine on the test. You're going to know periodic trends. Okay. All right, I'm going to come back and do